Hi, in this video I will show you how to use our graph super resolution network code to predict a high resolution brain connectome from a given low resolution brain connectome. This work has been accepted to the Machine Learning in Medical Imaging 2020 workshop, and it is part of my research project at Basira Lab. First, we will install PyTorch and other dependencies we need to run our graph super resolution network code. Second, we will go over data representation, how to simulate data, and how to download the original dataset of the paper. And finally, we will execute the training and testing of our model. To install PyTorch and other packages, if you prefer to run the code on Colab, all packages mentioned below are already pre-installed. Otherwise, preferably inside a virtual environment, you can run the command pip install torch vision. For more information, visit the link. Next, you can type in the following commands to install NumPy, scikit-learn, and SciPy. To download the GSR-Net code from our GitHub profile, visit the following link. Before running the code, I will show you how your input data should be represented. Firstly, each subject is represented by two separate functional brain networks of two distinct resolutions. One, the low-resolution brain graph, and two, the target high-resolution graph. Each brain graph in itself is represented by a set of nodes and a set of edges, where a node is defined as a brain region of interest and an edge is defined as the connectivity weight between two regions of interest, using a specific matrix, such as correlation between neural activity or similarity in brain morphology. Thus, for the low-resolution brain graph, the connectivity or adjacency matrix is an L by L matrix, where L is the number of nodes for the low-resolution connectome, and for the high-resolution brain graph, the connectivity matrix is an H by H matrix, where H is the number of nodes for the high-resolution connectome. The entries in both adjacency matrices represent the connectivity weight between two nodes. Our graph super-resolution network aims to predict a high-resolution graph as topologically similar to the target high-resolution graph as possible. For our dataset, we need in total n low-resolution adjacency matrices of dimensions L by L and n high-resolution adjacency matrices of dimensions H by H. To simulate the dataset, you can generate n random matrices of the specified dimensions. To evaluate our framework, we use five-fold cross-validation strategy. In the training process, we feed low-resolution connectomes and the respective target high-resolution connectomes for all training subjects. The testing process evaluates the mean squared error between the ground truth high-resolution graph and predicted high-resolution graph for all testing subjects. If you want to use the dataset in the original paper, download the SLIM dataset from the following website provided in the link. In the web page, find the available derivative connectivity matrices and download the subjects shown below. Extract the downloaded tar.gz folder using extraction tools such as 7zp. Make sure to enter the correct path of your dataset folder in the file preprocessing.py. To run the code, you can use this command and input the arguments according to your data and preferences. To learn more about the arguments and how to use them, you can add the setting Help. For more, please visit the official GitHub repository of GSR-Net.